Okay. So these are the lecture tasks for today. They look a bit different because here I didn't delete the code. So basically you have the solutions right away, which is kind of an oversight. I forgot to delete it in the other lecture tasks, and now it's too late because I already set up the GitHub classrooms. But if you want to follow me, and I think it's very, very good if you type this in yourself, you can just delete it. And then maybe a couple of things to remember or from yesterday. In the very end, if you remember yesterday, we tried to export a CSV file or election table, and we got a warning message. And I was a bit surprised because initially I thought it was an error message and not a warning message. So there is a difference between warning messages and error messages. And error messages mean that your code has that the parser has encountered an error while executing your code, and then the code will be terminated so you don't get any results. And you have to fix the error source before you can run this code. A warning message warns you about something that might go wrong with your code, but it still executes the code and you will still get a result. The result may be messed up and not as you intended it to look. And it may not look as you intended it to look like, but it will still run. But still, you should try to address warning messages when they came up. Yeah, as I said before, today we have a little bit of statistics, but it's super short. It's basically just this little part here. It's very negligible. Tomorrow we have a bit more and in-depth statistics. Today we just have a little bit, a tiny bit, just to get you hooked. That's not something I thought I would ever say. But most of the time today we will spend on plotting and exploring the basic plotting functions that R has to offer. But we start off, we get the statistics part out of the way. And first, we didn't prepare any external data sets to show this on, so we create some. These are just two data sets we simply create by using the combine function, and here the sample function. The combine function you already know, and you should be able to tell what this code does. It basically combines a lot of characters, strings, red, blue, green, blue, blue, red, and so on, into a vector. If we run this, we will see we have here a vector, which is kind of like a list. And the vector contains our, it's not values, it's characters, red, blue, green, and so on. If I run this here, you will see it down here in the console. So this is the small thing we created. And then this function you don't know yet, it's sample. Actually, can we just write the question mark sample? Does it work like this? Yeah. Yeah, before we always used the help function like this, by writing help and then putting the function we need help on into the parentheses, into the brackets. But you can also write this just a question mark and then the function name. You can also, if you don't want it in your script, you can also write it down here. It's one of the few cases where it's probably okay to write directly into the console, like this. Yeah, the help page is already open. That's why you don't see anything. But the sample function takes a sample of the specified size from the elements of X using either with or without replacement. And we can create, we can sample out of a sequence, which is what we do here. We basically, maybe it's clearer if I run the code right away. What we do here is we define a sequence from 1 to 100, 100 as indicated by the double dot. And then out of the sequence, we take 100 values. And the values are random, which is replace true in this case. So our output is same as up here, a vector, but it contains 100 values that are randomly sampled out of this sequence. Looks like this. So it's just 100 random values. Yeah, doesn't have any purpose except that we now can use our basic statistical metrics on it, like we can calculate it. So you have a couple of functions to calculate these statistical metrics. That's very ordinary stuff like mean, median. Summary you already know, we had this before. These ones are new, standard deviation and variance. And the way this works is super easy. It's like in every function, you just take the function and say what data set do you want to have a function used on. Let's start doing it on X, which is this one with the reds and blues, the character with the characters. And let's see what happens if we run it on X. We get a warning message. The result of this is NA, so not available. And then we get a warning message in the mean function. The argument is neither numeric nor Boolean. So return NA, which is in German. But the same error message will show up for you. So it basically tells you you cannot calculate the mean out of X because X is not numeric or Boolean. Boolean would be false or true, which makes sense. So we can't do it with this vector. But if we use this function on our other vector, which is filled with integers, and integers are numbers, whole numbers, in fact, and not decimals, we will receive a mean value, and our mean value is a decimal. It's 49.14. This is our mean. We could also write this into an object if you need to save it for something. Then we have it a simple value into an object, but we don't do that for now. Now we have median. If we use median on X, this will work, I think, actually, because the calculation of the mean requires a mathematical operation, but the median is just the value in the middle of the list of the vector. So it goes to the list and checks which value or which entry is in the middle, and that is green. So the median value is green. That really doesn't tell you anything about the data set, but it's perfectly possible to use a median function on a vector that's made out of strings or characters. If we use it on Y, it works exactly the same way. It takes the middle value. The middle value is 48. So this should be relatively simple. Then just as a reminder, the summary function gives you out the summary of your data set. The summary can look quite different depending on what data set you use it on. It looks different if you use it on a data frame or on a matrix or on a vector. In this case, if we summary X, it will show us the length of our vector, which is 13, which you can also see up here. It's a sequence from 1 to 13. The class is character and the mode is character 2. So these are words. Okay, if we use summary on Y, you will get a couple of statistical values calculated for you. The minimum value, the first quantile, the median value, the mean, the third quantile, and the maximum value, which is super nice and saves you a lot of effort. You don't have to use this mean and median function. You can also just use summary and like look at it here. If we use standard deviation on X, we will again get an NA because It's not a numeric value, it's a character value. If we use it on Y, we get the standard deviation. And then we have variance, and it's the exact same thing. If we use it on X, we get an NA. If we use it on Y, we get the variance. So there's a function called table that you can use to display a vector as table. It uses cross-classifying factors to build a contingency table of the counts of all combinations of factor levels. So if you want to count how many blue values, green values, and red values you have, you can use table on X. And you can also convert this table into a data frame by using the data frame function, which we already used, I think, yesterday. I'm not entirely sure if we used it, but I think you know this already. Yeah. This is one way to do it here. Another way would be we write the table X into an object called table X, and then we don't call this function inside of a function, which we call nested functions, by the way. If you have a function inside of a function, it's called nested, which is a nice word, I think. But you could also call the object, the variable we created, into the data frame function and create this data frame like this. It doesn't really matter. All right, so we leave it like this. It gives exactly the same output. Yeah, if you have a nesting function, the function inside of the overload function will be executed first. So it calculates a table for X, and then it converts it into data frame. And then it assigns it to a variable called Z, which looks like this. We have an X column which says blue, green, or red, and then we have the frequency here, which is 6, 2, and 5. So this might be helpful if you want to count values. Yeah, just a bunch of basic statistical metrics you can calculate very easily calculate using R. You can also, if you have a data frame, calculate these metrics for columns. So yesterday, if you remember, we don't have this data frame here right now, but yesterday we had this data frame called Geo.Bonn, and it had a lot of columns for different parties. And you could also calculate the mean for one column or for one row, even though it would make no sense, I think, to do it for a row. But it's perfectly possible you can do this, just so you know about this. Okay, but with this in mind, do we have any questions for this, like regarding this part? If not, I will just go on to the plotting. You know what a plot is. This is kind of redundant information. Plot is a visualization of a data set that can look very differently. Usually we refer to every kind of visualization we do in R as a plot. So a map is a plot too. The graph is a plot. Everything is a plot. I've already shown you this cheat sheet for the base R plot functions. So you can always get back to that, like look over that if you're not sure what to do. But this cheat sheet is just for the basic R plot functions. Because plotting is so very important for publications, for example, and visualizing data, visualizing. I got it, visualizing data. There are a lot of libraries and packages that extend the plotting capabilities of R. And I think one of the most well-known ones in R is ggplot2. This is the same for every program language. So I think John knows some Python. You probably know like matplotlib and all the stuff from Python. Those libraries also exist in R for the most part. In R, the most well-known one is probably ggplot2. We don't work with that in this course because it has a very dedicated syntax, which is different from the R basic syntax, so the way we use the base functions. So here we only work with the base functions so far, which are quite limited or can be quite limited at times, but it's still, I think, worthwhile to look at them to like figure out what's the process behind plotting. So let's take our data set Y, which is this sequence from with 100 values, like randomly sampled values, and just use the plot function on it. And then you can see it creates a scatter plot with X and with an index value and the Y value. It's not super descriptive. Our data set is basically nonsense. But the index is just the position inside of this list or inside of this vector, and the y-axis is the value. So at position 1, we have 41, which is here. Alternatively, you can plot a histogram using the hist function, which would look like this. I hope you all know what a histogram is. But if you don't know it, it's the distribution of values throughout the data set. So the frequency. So you can see we have, I don't know, values between 0 and 10, like 12 of them. No, it's like 11 values between 0 and 10, and so on. You could just read this. It doesn't make a lot of sense. It's just to illustrate that we can create histograms in R. So to get away from these basic nonsense data we created up here, we have provided temperature data inside of the project, which I will now load into our. Okay. It's super helpful. Apparently, if you clone a project from GitHub, already sets the working directory to the project folder, to your local repo, so you don't have to adjust the working directory. So this should just work like this. And like this. So we use the relative file paths here. We don't use the absolute ones. We learned this yesterday. We can check these two tables. One is called Climate 2018, one is called Climate 2021. And those, I think it's temperature data from Bonn. Yes. And it contains a couple of columns. One is the station ID. So this is all the same. It's one station. This is the date. I think it's over the course of a single day. It's the same day, yeah. Like we have the precipitation in millimeters, which is Niederschlag, mm. We have the winter temp, which is mean temperature, max temp, which is maximum temperature, and min temp, which is minimum temperature. So these are individual days. I lied to you. It wasn't over the course of one day. It was over a couple of days. So these are over the course of 1, 2, 3, 4 months. And then we have the Climate 2021 table, which looks exactly the same, except that the data set is from 2021. And it's the same time span. Yeah, we have many options to plot data. Some of this you already seen before. We have this plot function, we have histogram function. Often you don't want to plot the entire data set, but we can show you how this looks like. If I just take this data set and plot it with the plot function, you get a bunch of plots, which looks very overwhelming at first. So this is basically the plot function not knowing what specifically to plot, and like plotting all kinds of different columns against each other, which some of them are like actually interesting data. Others, as for example, the station ID is not very interesting to plot because it's the same number the entire time. So you just get these very static looking plots. So maybe it would be smarter to plot one column. We take this middle temp, which is the mean temperature. You reference it the same as you reference a column in a data frame in general using the dollar sign. You could also use like a square bracket if you knew which column number it is. It's 1, 2, 3, 4. So you could use this alternatively. It makes no difference. We use this because it's easier for us. And we run this plot function. And then you can see here, we have maybe a bit more meaningful plot. We don't know what the index is here, but we can see the mean temperature on the y scale, on the y-axis. And we can already see quite a bit of fluctuation here. So it goes up, it goes down, and then it goes up. But of course, this is not super descriptive yet. It has no real labels. It has no color, and the axis labeling is like not very descriptive. So the idea of plotting in R is we have this plot function and we keep adding arguments to it. There are a lot of different arguments. You can look at them if you get help for the plot function. You have X and Y, which is basically determines the X and the Y axis. Then you can give the plot type. So if you give P, it becomes a point plot. If you give L, it becomes a line plot. Then we have stair steps. We have H for histogram. Then we have main, which is the title of the plot. We have sub, which is a subtitle for the plot. We have xlab, which stands for x label, which is the title for the x-axis. We have ylab, which is the same for the y axis. We have asp, which is aspect ratio, and so on. There's also a couple more arguments. So there's like there's a lot of arguments for this function, and you can see many of them in the spreadsheet, in the cheat sheet. I'm sorry, the cheat sheet we put into the folder. So here we have a couple of arguments. We will go through them one by one. By the way, a really good way to make a function with a lot of arguments more readable is to give line breaks after each argument. So like this. So now you have each argument in a different line. It's much easier to read, in my opinion, and it will still read the same function. Now you have to control enter at the very end of the function. If we do it like this, where's the labeling? Okay, yeah, we will work on that later. If we do it like this, we can see what our different arguments here do. So first, you define which data you want to have plotted, which is climate 2018, the mean temperature. Then you define a type, which is L. L stands for line. So this is a line plot and not points, for example. xlab is the X label, which is beginning of season. ylab is the temperature in Celsius. Axis equals F means the axes are not displayed. If we put it on axis equals true and run it again, you will see the axis labels are displayed. So you can use this at your own whoa, that's not wrong. It's very wrong, like this. You can use this at your own discretion. Y_lim stands for Y limits, and it gives an upper and a lower bound for the y-axis. So if we combine here -20 and 40, our y-axis will start at -20 and end at -40. We could do the same for the x-axis by using xlim. Oops. Exactly the same way. So maybe if we just want this from 100 to 300, that's like, yeah, don't forget, if you put a function like this, don't forget to separate your arguments with commas. But now we only have this specific part of the y-axis, of the x-axis in our plot. And then main is the title. So now you have already a basic plot. Here's a short description of the individual arguments. Now we have, maybe we just do that in English, right? Summer, fall, winter. Now we have a kind of important thing to know. We have our plot now, and if we want to add more stuff to this plot, we just run functions after that, and it will be added on the same plotting window. So if we do this, it doesn't do anything. It just enables the axis. I have to turn it off so you see what I did. I turn off the axis here by using the axis equals false argument, and then you can individually turn it on by using the axis side equals 2. So now you get the y-axis, and the idea here, I think, is to basically create a plot where we can see the temperature, the mean daily temperature for each season. And you can add this by using the axis command and then giving, I just use the help function and show it to you. So axis adds an axis to the current plot. If it doesn't have one, it works. Otherwise, nothing will happen. But if you don't have an axis, you can use the axis command to add an axis. And this is preferable to using this, for example, axis equals true, because you can alter the axis, which you cannot really do in the inside of this plot function. So often you will plot the function, you will plot data without axes and then add them individually. And the idea here is to create a plot that shows the seasons on the x-axis and the mean temperature on the y-axis, and that's why we turned off our axis in the plot function, and now we add them individually. Sorry, it was a bit confusing at first. I had to think about how I express myself. Sorry, I wanted to keep this open. And this axis function has a lot of different arguments as expected. The most important one is side. Side specifies which axis will be plotted, or on which side of the plot our axis will be plotted. So if we put side equals 2, it will be the y-axis. If we put side equals 1, it will be the x-axis, which is also why here is a little 1. If we put in 3, it will be up here. If we put in 4, it will be up here. And as you can see, it just keeps adding axes if you rerun this function. So now we have kind of destroyed our plot. So I run the plotting function again and build it from the ground up. And now we create this little side axis without any further specifications, because this is already quite nice. And now we add the individual seasons, and for this we kind of need to know when the season ends inside of the data, and then you can specify the position where the label is supposed to be. Spring is supposed to be at position 79, summer is at 171, and so on. If we just run this, you will see what happens. It will put a label called spring, beginning of season, at the position 79, which is, I think, the 79th day in the year. And then we have summer, fall, winter. All right. Still, we can work more in this plot. We can make it even better by adding additional lines. And the command to do this is appline. Again, I will just use the help function to show you what it does. And the appline function adds one or more straight lines to the current plot. So it's literally just, it adds a line at the position you give it. And here you can give a couple of different stuff. You can give the intercept, so where it's supposed to intercept another line, the slope, the y and x values for horizontal and vertical lines. Sorry, I forgot to tell. The first argument is side. So it's basically the same as here. If I put this away, this is the same. So if you put a 2 here, it will put it on the y-axis, which is already taken right now. Here, you can see it here. If I put in 3, it puts the spring label up here. So the first argument is side. So maybe to make it a bit more clear, I put it like this here. Yeah, so the first argument here is which side of the plot should the axis label be generated. And now I ruined it again, so I will just keep rerunning it. There we go. Okay, but back to the appline function, we can add a lot of different straight lines through this plot. Not all of them make sense, of course. And the arguments we have here is A, B, V, and H. And those are already explained in the comments. So A is the intersection with the y-axis. B is elevation. V is a vertical line on a certain y value. And H is a horizontal line on a certain y value. So we just start by doing appline H equals 0. And then we get a horizontal line through the y value 0. If we use appline vertical, V stands for vertical, and 79, we will get something like this. So now it's there's a small little typo here. This should be vertical line on x-axis. So now we get a vertical line through the x value 79, which is exactly the start of spring. And for the other beginning of seasons, we can do the same, just to bring some more clarity into our plot and make it clear which brackets are which seasons. And then you could also add more information to the plot, more information to the plot itself by adding more data. So if we want to add more data, we don't want a straight line, we want more data into our plot. For example, here it would be quite nice to not only have the mean daily temperature, but also the maximum daily temperature and the minimum daily temperature. And we can just add this using the lines command, which is different from appline because this time we add actual data and not just a straight horizontal or vertical line. Lines works like this. It's basically the same as in the plot function. You just define the data you want to have plotted as a line, and you define the type, which is L. For lines, and then you can define a color if you want that. So we just run this. If you remember in this climate 2018 data set, we have one column called max temp, one column called min temp. We just run it for both and add our maximum temperature here and our minimum temperature down here. So yeah, and it's pretty much what we would expect from Bonn. We have a cold winter, and then rising temperatures in spring, and the highest temperatures in summer, and then in fall the temperatures decrease again. There's a lot of other design choices you could do on your plot. For once, you would probably change the title now because it doesn't only include mean daily temperature, but maximum and minimum too. And you would maybe also have a legend. But for that, you can check out the cheat sheet and like play with the different options by yourself. Just one important thing, you can import this, you can export this, sorry, not import, export. You can export this plot very easily. Oops, there's a small export button here, and you can save it as an image and save it as a PDF. And then if you, and that's a very common approach, if you're not really good at plotting, you can do as much as you can in R, export this plot as an image or as a PDF, and like continue working on it in image editing software, which is something that's a lot of people do. It's nothing to be ashamed of if you're really good in like Photoshop or like other image editing software. And sometimes this little plot window has issues, and I don't know where they're from, but often it helps to restart the plot window. You can do this by clearing all plots and then trying to plot your plot again, like this. Or you could turn it off by using this code here, def off. It's a function to turn off the plot device. And then it gets turned off. It's kind of a restart, and often it fixes issues, that random issues that come up with the plotting. So if you try to plot something and it gives like a super weird warning or error message and it doesn't really work, try this before you blame yourself and your code. Often the code is correct and it's just R being a bit mean. Okay. So this is one line plot, but another common way of displaying or visualizing data is scatter plots. You've already seen a short one before. For a scatter plot, you need two values, two sets of values to plot against each other. And a scatter plot in R is super easy to do. You basically use the plot function, and then you give both data, in this case columns, but they don't have to be from the data set. It could be from different data sets too, that you want to plot against each other and separate them with a, how's this symbol called? The little wave, tilde, with a little tilt, like this. In this case, we want to plot the maximum temperature against the precipitation in millimeters. And if we just run this, we get a scatter plot. And down here, you have the precipitation, and up here in the y-axis, you have the maximum temperature. And what you can see here is there seems to be like a very small connection between the amount of precipitation and the maximum temperature. It's very insignificant. This plot isn't super helpful, but it's just so you know that how it works. Well, then one question I wanted to address, I have to go a bit back, but somebody asked me in this part how we know, for example, that I will get this plot back in. So sorry, we take a small step back, but I just remembered how we know that spring starts at x equals 79, that summer starts at 171 and fall at 265. And I apologize, it's a bit of meta knowledge because I know the data set, so I forgot to explain. But our climate 2018 data set has 365 observations, so 365 rows. And you can already imagine it's one for each day. So if you go in here and you go, you look at the number, the row 79, you will find it's like the 2nd January, February, March. So something like, no, it's 20th March, which is, I think, the beginning of spring. I'm not entirely sure right now. I don't have my meteorology straight, but yeah, you get the idea. You have here dates, and you can kind of find out which is the beginning of each month. It depends a lot on where you are on the world. Obviously, some places have different seasons or no seasons at all, or very small seasonality. So yeah, but in this case, where we have a plot, where we have a data set with 365 entries, and each entry is for one day in the year, it's very easy to find out. But I kind of forgot to explain that, so now you know. Okay, so this is a sequence indexer. You know this already. You know how to define a sequence with the double dot, a linear sequence, and you know how to index a plot. And in this case, it limits our data set from precipitation in millimeters from the whole data set to the first 111 entries. And the reason we do this is because our climate 2021 data set is not available for the entire year. So it's only, I think, the first 111 days or something like this. So that's why if we want to plot them against each other, if we want to compare the precipitation in 2018 and 2022 and this time period, we have to adjust, basically, or we have to index the same data size and the same area for, or same temporal range. That's what I want to say, sorry. So this is just the same function again. It's a scatter plot, but this time we don't, we use it on two different data sets, climate 2018 and climate 2021. And in the same column, they both have the same precipitation in millimeters column. And it's kind of, you can compare the precipitation in millimeters now between 2021 and 2018. And all in all, I think you can see 2018 was a lot wetter. So in the same month here, there wasn't as much, or in the same time frame here, there wasn't as much precipitation in 2021 than it was in 2018. That is important. That is, it has to be here. It has to be here. If you have two value sets and you try to plot them against each other in a scatter plot, then of course both value sets must be of the same size. You don't necessarily have to subset and like alter your data set to make it fit, but and often you can just index the correct part when it comes to date, that is, when it comes to time. And what's this? Oh, this is just the mean temperature of, this is just, we plot them against each other, but this time in a line plot. So we go one step back basically and yeah, get rid of the scatter plot and like plot the mean temperature in 2018 in the first 111 days as green, which is very ugly and hard to read green. Maybe let's change it to blue, like this. And then we just, using the lines command, we just add the mean temperature in 2021 over it, so we can compare the two. And yeah, here you can compare the differences in mean temperature in the first 111 days in 2021 and 2018. Yeah, that's just so you know how it works. But this, I think, shouldn't be here. It should be in the lines plot section, maybe like here. Placeholder comment. All right, so that was not box plots. That was scatter plots and line plots, and then we have a third kind of plot that's super common in scientific data or scientific releases, publishings, and that is the box plot. And I think that's really good to know how to create one, because it's really, if you ever try to create a box plot in Excel, for example, you know that it's really hard and not very user friendly, especially compared to R, in my opinion. I hope you know what a box plot is. If you don't know it, look it up right now after the course. A box plot or box whiskers plot looks like a box with two whiskers, and it doesn't really matter if it's horizontal or vertical, because it's like the data is displayed one-dimensionally, and the whiskers denominate the quartiles, and the boxes are the middling quartiles, and there's always a line in the middle, which is the median value, and then there's like confidence intervals. You can get like most basic statistical metrics just by looking at a box plot, which is super important. It gives you a really good overview of how your data is distributed. So it's often something that's not necessarily in the final release of a paper, for example, but that you do for yourself to kind of find out how your data is distributed. Then here again, I would put the arguments like this to improve the readability. And this can be definitely can be in the same line. There we go. There we go. And the command to create a box plot is box plot. It's a recurring theme in this course, that the functions are named after the stuff they do. And for a box plot, you could also just create one box plot. In this case, we create box plots for both data sets, but only for the first 111 days. Again, because climate 2021 only has 111 observations. So we kind of try to adjust to that. And I just run this, and we look at our box plots. The colors are very ugly, obviously, but we can play with it a little bit. What we do here is we give them our data sets that we want to have plotted. Climate 2018, mean temperature, the first 111 values, and climate 2021, mean temperature, which only has 111 values, so we don't have to specify this. It's only that they have the same size. Then we have an argument called notch. And notch just basically defines if you have a notch or not. If you put it on false, it doesn't have a notch here. The notch is the mean value. That's so you can see it easier. Then these are the colors, green and red. The base colors that are used are very strong and very neon and very bright, neon bright. But we will learn how to manipulate colors, I think tomorrow, not today anymore. By default, R has a bunch of basic colors like green, red, black, white, yellow, that you can just use by using the names. And for now, we will stick to that. But you can also define your own color ramps and color presets and give your plots custom colors. That's very much possible. For now, we leave it like this, except we change the green to blue, because green and red is not colorblind friendly at all. Then this again is mean temperature, and the x-axis is just 2018, 2021. All right, we adjust it like this. What does this do? Oh, it adds the median values. Okay, so I talked. I lied to you. I said the notch was median, but the notch is mean, and the median value we just add here. We changed this to blue too. Maybe that's not the best way to do it, but we just use the appline command here to create two horizontal lines at where the median of the blue box plot and the red box plot is in the same colors as those box plots. I think it's not super good to read, even if we export it. Yeah, well, then it's a bit better. If we increase the size, it's a bit better, but yeah. Just so you know, it's a possibility. You can use appline in every plot, even box plots. It doesn't matter. You can create lines wherever you want. Okay, but these are basically box plots 101. Very fast, very rough around the edges, but should be good for now. And then we have yet another kind of plot that you can create here, and that's a histogram. And we already showed this one in the very beginning with this little line where we had applied the histogram function hist on our little mockup data set. Now we will use our function on real data on the climate 2018, mean temperature, and then the first 111 entries again. And then if you interpret this, down here you have the mean temperature. Here you have the frequency, and you can see the most frequent temperatures in this date or like temporal range. So in the first 111 days in 2018 were around 5 to 10 degrees Celsius, which is kind of what you would expect from the beginning of the year in like Western Germany. You could also set the amount of breaks by using the break argument. This kind of gives you the option to control how granular your data is displayed. So if you have a high amount of breaks, you can see more differences. If we tune this up to like 25, our histogram looks like this. Maybe 50 like this. At some point, it doesn't improve the plot and just hurts readability, in my opinion. So let's keep it at 20 at max for here now. Yeah, and what you can see here is a bit, it's not entirely normally distributed, but kind of. The extreme temperatures, extreme -5 and 20 degrees are very rare in this first 111 days in this year. And the moderate temperatures are really common. It's kind of what you would expect. You can also plot two histograms together in one plot. In my opinion, there's not a lot of cases in which that is beneficial, but sometimes you kind of want to compare the distribution of two plots, of two data sets, sorry, in two plots. And for that, you need two plots. The first thing we can get away from here is you can also write your plots into variables. That's very much possible. You can assign your plot a variable. In this case, hist 2018 and hist 2021. And then it's, if you use the argument plot equals false, this function won't be plotted in the plotting window. It will just be stored. The result will, the plot will just be stored in the variable with the same name. It's just a list basically with parameters. Okay, but if we put this on true, it will show up here. But for now, we keep it on false because we want to do some different stuff. Okay, I lied again. I said we do colors tomorrow, but we actually do it today, at least a bit. You can define your own color ramp by using a function called RGB, which stands for red, green, blue, which is, I think you know this, but it's a common way to denominate color by giving the amount of red, green, and blue, and then additive mixing. And using this RGB function, I once again open the help window so you get to know which arguments we have inside of this function. You basically, inside of this function, you have to define how much red you want to add, how much green you want to add, how much blue you want to add. The alpha is how transparent your color ramp should be. So if you put the alpha on 1, I think it's not transparent at all. And if you turn it down, the color ramp becomes more and more transparent, and that means you can see the background through the colors. And then the name is the name of your color ramp, which you define, and then you can use it as, for example, as we used blue here or red. Okay, so we define our color ramp here with the following values: the RGB values, red, green, blue. The max value basically gives you how many different shades of your color ramp should be included in the color ramp. If you do 255 is 16-bit, I think. Or like 8, not entirely sure, but it's a very common value. Alpha equals 100 means it's not going to be transparent at all. It's going to be a solid block of color. And then the name is just so you know which name it is. It's light green, and in this case, it's light pink. So we define these color ramps, and then they show up here in a very weird format. It's something that looks very weird. This is a hex code. That's another way of expressing color. Each color imaginable by humans has a little hex code, and you can look up the hex code for every color online too. So this is just a way to reference colors. And then if we want to plot our histograms against each other, we can just plot them using the plot function, and then it again asks for color. Maybe we do it like this because we did like this before. It asks for your color, and instead of like saying red as we did before, we use our color ramp C1. And this is just the Y elements. We will see why we do this when I plot. One important thing is this little argument here, add equals true. Add equals true. If you use it in a plot function below another plot function, it means what you plot here will be added on the plot of before. If you don't do this, both of your plots will just override each other. So if we plot this and our little color ramp here, you can already see it's the same color as before, the little light green. And if we now run this without the add equals true, it will just create a new plot. But if we add it like this, it will be plotted all over it, which is not very helpful because it's yeah, doesn't really work right now, right? Like this. There we go. Sorry. Sorry. I had to run that anew because yeah, funny stuff happened. And what you can see here is both of our histograms are plotted over each other. And we can easily see in which value ranges we have differences between the both data sets. And what you can basically see here is that the values between 0 and 5 degrees Celsius in 2021, which is this little salmon pink colored bar, are much more frequent. But in other value ranges, for example, -5 to 10, it's much less frequent. So you can see the difference in distribution. It's not super optimal because the overlay creates a weird brownish color mix, but it shows you in which brackets, in which value brackets, the plots differ from each other very fast. Okay, I hope that was understandable. I think that's already the end of this little script here.